June 22, 2026. Astronomers published the chemical fingerprint of an object that did not form around our sun. It crossed the darkness between stars, entered the solar system once, and is now leaving forever. Its name is 3I Atlas, the third confirmed interstellar object ever seen. It looks small in every telescope image, a bright nucleus hidden inside a cloud of dust and gas.
But the water escaping from that cloud carries a message. Its isotopes do not match the water in Earth's oceans, the ice in familiar comets, or the material from which our planets form.
The difference is so large that researchers traced it to temperatures below 30 Kelvin in a cold and relatively metal-poor environment. Their models allow an astonishing possibility.
3I Atlas may have formed 10 to 12 billion years ago, long before Earth, long before the Sun, perhaps when the Milky Way itself was still young.
That does not make it an alien spacecraft. The evidence says something stranger in a different way. A natural fragment of another planetary system has passed close enough for us to read its chemistry. So where did it come from? Why did radio telescopes examine 74 million signals around it? And what exactly did this ancient visitor bring into our solar system? The story begins on July 1, 2025, at an Atlas survey telescope in Rio Hurtado, Chile. Its cameras were designed to find objects that move against the fixed background of stars. One faint point refused to fit an ordinary solar system orbit. As more observations arrived, the path became unmistakable. It was hyperbolic, an open curve, not a loop around the sun.
Planets, asteroids, and ordinary comets remain gravitationally tied to the sun. Trace the orbit of 3I Atlas backward, and it does not return to the distant edge of our system. It continues into interstellar space.
Astronomers searched older images. The object had already appeared in archive data before anyone knew what it was. Every earlier detection extended its path and made the interstellar conclusion stronger. The name records the discovery. Atlas is the survey that reported it. The letter I means interstellar, and the number 3 means humanity had confirmed only 2 visitors like it before.
It was never a danger to Earth. Even at its closest, it remained about 170 million miles away. The urgency came from a different fact. This was a sample from another star system, and it would not stay.
The first known interstellar object was 1I Oumuamua, discovered in 2017 after its closest pass to the Sun. It showed no obvious coma, had an unusual shape or brightness pattern, and left astronomers with little time to study it. The second was 2I Borisov. Found in 2019, it behaved much more like a familiar comet, complete with gas, dust, and a visible tail.
3I Atlas arrived with one enormous advantage. It was identified months before perihelion, while it was still approaching the Sun. Observatories could plan instead of merely reacting.
Its exact solid nucleus remains hidden in the coma. NASA's early constraints allowed a diameter anywhere from roughly 440 meters to 5.6 kilometers. That uncertainty matters. A bright coma can make a small nucleus appear enormous. What telescopes see is not a clean rock in space, but sunlight scattered by material released around it.
Yet even the smallest estimate represents a physical object assembled around another star. Not light from an exoplanet, not an indirect atmospheric signal, material from a foreign planetary system passing through ours.
Within weeks, Hubble tracked the moving comet and recorded a teardrop-shaped cocoon of dust. Because the telescope followed 3I Atlas, the distant stars stretched into lines behind it. Then an extraordinary observing campaign began. Webb and Spherics studied its infrared chemistry. TESS followed its brightness. Lucy, Psyche, Parker Solar Probe, and Europa Clipper turned their instruments toward it.
Spacecraft at Mars joined the campaign. MAVEN measured the coma. Mars Reconnaissance Orbiter watched from millions of miles away. Even Perseverance paused its work on the surface to photograph a faint interstellar smudge in the Martian sky.
The European JUICE spacecraft had a rare angle after perihelion. Its cameras captured a structured coma, a long tail, jets and streams of material. In 53 navigation images, the visitor moved against a crowded starfield. This was not one perfect close-up. It was something more scientifically useful, many imperfect views, taken at different wavelengths, distances, and positions across the solar system.
Each instrument saw a different layer of the same event. Motion revealed the orbit, images showed dust, spectrometers separated molecules, radio telescopes searched for narrow signals that nature rarely produces.
The word interstellar changes how people look at an object. If nature can throw rocks and comets between stars, a technological civilization could, in principle, send hardware along similar paths. Our own Voyager probes will eventually become interstellar artifacts. To a distant observer, they would be artificial objects moving through a planetary system that did not build them.
That makes every interstellar visitor a reasonable target for a technosignature search. It does not make every visitor a plausible spacecraft.
For 3I Teles, the direct observations show familiar cometary behavior. Solar heating drives gas and dust from the nucleus. A coma forms. A tail points away under the influence of sunlight and the solar wind.
No maneuver has been measured. No structured transmission has been found. No image reveals machinery. The artificial origin idea is a question that instruments can test, not an answer supplied by the word interstellar.
And that distinction improves the mystery. We do not need to turn 3I Tatlis into a spaceship. Its measured chemistry already describes a place that has never been seen. As 3I Atlas rounded the sun and began its outward journey, ancient ice warmed and became gas. That expanding coma gave the James Webb Space Telescope a temporary laboratory. Webb's spectrographs did more than take a picture. They separated infrared light into chemical fingerprints and mapped where different molecules were concentrated around the nucleus.
Water vapor extended far into the coma, much of it released by icy grains. Carbon dioxide remained unusually abundant. Methane was concentrated closer to the hidden nucleus.
The methane detection was the first direct measurement of that gas in an interstellar visitor. Its delayed appearance suggested that some methane ice had remained protected below the upper surface until heat reached deeper layers.
None of these molecules proves life. Water, methane, and carbon compounds can form without biology. Their importance lies in their ratios. The recipe is different from the recipes measured in most solar system comets.
Then Webb and ALMA found the detail that transformed the story from an unusual comet into a preserved record of another time. Ordinary water contains 2 hydrogen atoms and 1 oxygen atom. But hydrogen has a heavier isotope called deuterium, whose nucleus carries an additional neutron.
Replace 1 hydrogen atom with deuterium and the result is HDO, often called semi-heavy water. The proportion of HDO to ordinary water depends strongly on the conditions where the ice formed.
In solar system comets, semi-heavy water is rare. In 3I Atlas, ALMA found a proportion at least 30 times greater. Compared with Earth's oceans, the enrichment was more than 40 times greater. There is an important technical detail. In that ALMA observation, ordinary water itself fell below the detection threshold. Researchers directly detected HDO and constrained the total water through methanol measurements and physical modeling.
Independent Webb observations also found extreme deuterium enrichment. Different instruments and analyses pointed toward the same broad conclusion. This ice formed under conditions unlike those that produced our comets.
Deuterium chemistry becomes strongly enhanced in intense cold below roughly 30 Kelvin. The ratio acts like a memory of a dark cloud or the remote outer region of a planet-forming disk.
The water was not manufactured during the comet's brief passage near our sun. It preserved a chemical setting from the system that built the object before something expelled it into interstellar space.
Water supplied one clock. Carbon supplied another. Webb measured unusually high ratios of carbon-12 to carbon-13 in carbon monoxide and carbon dioxide. Across cosmic history, generations of stars manufacture and redistribute heavier elements. Later planetary systems inherit a different isotopic environment from systems born early in the galaxy.
The low relative abundance of carbon-13 in 3I Atlas points toward a metal-poor formation environment before stellar evolution had enriched the galaxy to the level found around the Sun.
When researchers compared those ratios with models of galactic chemical evolution, the most ancient solutions reached 10 to 12 billion years. The comet may be a relic from the era sometimes called cosmic noon, when star formation was intense.
But the word may is essential. No instrument read a manufacturing date from the nucleus. The estimate depends on chemical evolution models, and the precise birthplace cannot be reconstructed across billions of years of chaotic gravitational encounter.
The cautious conclusion is still remarkable. The evidence strongly supports a cold, chemically distant origin. The most ancient interpretation would make 3I Atlas more than twice the age of the solar system. While optical and infrared telescopes studied matter, the Allen Telescope Array asked a different question. Was anything near 3I Atlas producing a narrowband radio signal? SETI researchers observed for more than 7 hours across frequencies from 1 to 9 gigahertz. Their pipeline registered roughly 74 million initial detections.
That number does not mean 74 million alien candidates. Radio observatories sit inside a storm of human technology: satellites, aircraft, communication systems, and electronics on the ground.
Automated filters removed signals that did not move with the comet or had obvious terrestrial characteristics. Roughly 200 candidates remained for closer inspection.
Every one was traced to human-made interference, either on Earth or in Earth orbit. No technosignature was detected.
The null result was still powerful. Across the observed frequencies, the search ruled out transmitters near the comet with powers of roughly 10 to 110 watts, comparable to ordinary household devices.
That does not prove no technology could exist in any form. It answers a narrower, testable question. There was no radio beacon of the type and strength those observations could detect.
For the first time, humanity could examine an interstellar object closely enough to reject a surprisingly weak transmitter. That capability may matter when the next visitor arrives. JUICE observed 3I Atlas soon after perihelion, when sunlight had made it highly active. Preliminary analysis estimated that it was releasing about 2,000 kilograms of water vapor every second. ESA translated that rate into an image, roughly 70 Olympic swimming pools of water per day, expanding into space as gas.
The tail, jets, and changing gas production all behaved as cometary physics predicts. As the object moved away and cooled, water production fell more sharply than the more volatile methane and carbon dioxide.
So the final evidence does not divide neatly into ordinary or extraordinary. Dynamically and visually, 3I Atlas is a natural comet. Chemically, it is unlike material measured in our planetary system.
The word alien is accurate only in its oldest meaning, foreign. The comet is foreign matter, assembled from another stellar environment and delivered without a spacecraft, sample return capsule, or human invitation.
3I Atlas did not bring evidence of organisms. It brought water, carbon dioxide, carbon monoxide, methane, and other volatile material whose isotopes preserve the history of their formation.
Those ingredients include carbon, hydrogen, oxygen, nitrogen, and sulfur, elements associated with complex and potentially prebiotic chemistry. Their presence does not demonstrate life, but it shows that chemically rich building blocks formed around other stars.
Normally, astronomers study distant planetary systems through photons. They watch a planet cross a star or read an atmosphere from a spectrum measured across light years. An interstellar comet changes the relationship. It is a piece of another system entering the range of instruments built to study our own. The sample comes to us.
We cannot identify its parent star. We cannot rewind its trajectory for billions of years, but its molecules still contain information that the original system wrote into the ice.
That is what 3I Atlas brought here. Not a message composed by intelligence, but matter carrying a memory. 3I Atlas is already leaving. Its open orbit will carry it beyond the planets and back into interstellar darkness. It will not circle the sun and return for another observation campaign.
The images, spectra, and radio data remain. More than a dozen missions turn toward the same fleeting target, creating an archive that researchers will continue to compare for years.
Future sky surveys should discover interstellar objects earlier and more often. One day, a waiting spacecraft may intercept a new visitor before it escapes.
Most will probably be natural. That is not a disappointing result. Each one is a preserved fragment of a different planetary system, formed under conditions we cannot reproduce and may never directly visit.
The question surrounding 3I Atlas began as a familiar one. Could this be technology? The evidence delivered a better ending. A normal comet crossed the solar system carrying abnormal water, ancient carbon, and the chemical record of a world system older than our own.
It did not transmit a message. It was the message.